Hey everybody, welcome back to this channel. In this video, we're just going to talk about alternating current. Oops, let me share this iPad screen here. Okay, so up until now, we've dealt mostly with direct current. So we call that DC, and that just means that current is flowing in one direction, more or less. Right, so on the lab benches, we've been using these power supplies, and they're more or less modeled with this voltage source, plus and minus, and the characteristics, right? So this voltage source is, at the moment we turn it on, it's just some constant voltage. I'll just call it VI. Right, and we can turn it off and on and kind of simulate this alternating pulse. And it's not even exactly alternating, it's kind of just going from an on to an off state. But now we will be introducing an alternating current source. And these can be specified as either sinusoids or pulse trains, a lot of different ways, but we're just going to start off by talking about a sinusoidal source. Right, so over time, it's got, if it's a real sinusoid or cosine, it's gonna, oscillate up and down with some voltage here. I'm gonna call it VAC maybe. And so there are a number of different things that you have to specify. First of all, what is the amplitude? And you can specify the amplitude as V peak, or sometimes shorthand VP. You can also specify the peak to peak, and so how far that distance is. That's V peak to peak. Or you can specify the root mean square voltage. And that's about here. So maybe I won't make that pink. That's kind of hard to tell there. Let's make it green. So this would be kind of like the peak to peak voltage, or not peak to peak, the RMS voltage. And so RMS is, if you had whatever sinusoid, well, let's just write it out. So VAC is equal to, VP times this cosine. Or it's actually a sine that I've drawn out. So sine of some 2 pi ft or omega naught or omega t, however you want to specify the frequency, right? And if you specify that it's this many volts, then it would be, to write it in terms of peak to peak voltage, right? Your amplitude would just be cut in half here. And I think the root mean square is, so you take the square root, you take the average, and you take the square root, right? So root means square, and you square one of these. I'm not exactly sure how to write it out, but we'll come back to that. But basically, in LT-Spice, it allows you to specify the peak voltage, and I'll go over how to use LT-Spice to do this. And so you've got a sinusoid, and it's got that peak amplitude, as we're used to writing the amplitude of a sinusoid. And so what kind of implications does this have? Well, let's just recall the RC filter that we were looking at, this low pass filter topology. We've got a resistor, we've got a capacitor, and you'll recall right? That over time, as current flows into the capacitor, the voltage of that capacitor goes up. So we've got VC, we've got ground here, and we've got over time, depending on the value of the resistor and the capacitor, it charges up asymptotically here to this, whatever this input voltage is. Right, and that's just when current is flowing directly into this top node here. Right, but what happens if we were to have an alternating current? Well, what would happen is let's call this VC2 and VAC. Right, so the capacitor may or may not have enough time to build that charge up, right? So if the current, is going this way, but it doesn't continue going into that top plate, for as long as it takes to get charged up, right? So let's say, at this time here, maybe this is like around 3 tau or something, whatever that RC time constant is. So at that time here, suppose the current all of a sudden switched directions, right? So this is a plot of VC, and this is a plot of VC2. So let's suppose that before we got to that 3 tau, the current started going in the opposite direction, right? So looking back at the alternating current sinusoid pulse here, when the polarity, right, when this AC voltage goes down, current will go in the other direction, since current likes to travel from high to low potential. So if that happens, the capacitor is going to charge up, going to start charging up, and maybe let's say at this point, current starts going the opposite direction, or not even that, let's say, yeah, so at this point, current starts going the opposite direction, but even as this, at this inflection point, the charge on that capacitor is going to start flowing off the plate. So maybe it'll just trace the input voltage instead of building up all the way as we had expected, 3 tau. And so for oscillating faster than that capacitor can charge, you can see that the voltage there is no longer going to come close to that, the magnitude of this alternating current at least. And so the amplitude, I guess, or yeah, the magnitude there. So hopefully that's sufficient to get started. I think the quiz should be hopefully pretty straightforward. In the next video, we'll go over how to use LT-Spice to, model these alternating current behaviors. And you're welcome to use that on the quiz. And also, you're welcome to use LT-Spice on the quiz and work together since we're not meeting this week. In other news, I've also posted a submission portal for the final project proposal. So thanks for tuning in. I'll see you guys next time.